Hello protein purifiers. In this video, I'm going to show you how to recombinantly express a his-tagged protein in E. coli and purify it using immobilized metal affinity chromatography. The first thing that we're going to need to do is make some media. For E. coli cultures, this would typically be LB media, or you could use 2YT media or terrific broth, depending on your specifications. I'm going to make some LB media. The recipe for LB is 10 grams of tryptone powder, 5 grams of yeast extract, and 10 grams of sodium chloride per liter, and I'm going to make a liter of media. The weights don't need to be exact here. Within 1/10 of a gram is all right. After weighing out the media components, always clean up the scales when you're done using them. We'll add distilled water up to a total volume of 1 liter. Keep in mind, this is distinct from tap water. Because my volume and concentration don't need to be exact for culture media, I'm not using a graduated cylinder. To dissolve the powders, I'm using a magnetic stir bar and a stirrer. It can take a little bit of adjustment to position the stir bar and get the speed right for optimal mixing. Once it gets going, it can take a few minutes for the LB to completely dissolve. When it's done, you can remove the stir bar with a magnetic retriever. With my 1 liter of LB media, I'm going to reserve 100 milliliters in a small bottle that I will keep at my bench for small cultures. The rest I will pour into a 2-liter Erlenmeyer flask, which I will use later for my protein expression culture. I'm going to sterilize these later by autoclaving. The autoclave operates under high pressure steam, so I don't want any bottles to be sealed airtight, otherwise they will get crushed by the difference in pressure and shatter. I'm keeping bottle caps loose enough that steam can get in and equalize the pressure. I label using autoclave tape, which will change color under steam pressure at high temperatures as an indicator that the items have been sterilized. When everything's ready, we can load the items to be sterilized into the autoclave on an autoclavable tray. Seal the chamber and set the program for liquid sterilization. The whole cycle should take about a bit more than an hour. The next step is to inoculate liquid cultures, assuming that you already have your expression strain transformed with a plasmid encoding your recombinant protein on an agar plate. We'll start with a small starter culture that we will grow overnight, and afterwards, we'll use that culture to inoculate a larger expression culture. You want to pour 5 to 10 milliliters of sterile LB into a sterile culture tube. I'm using sterile technique at my bench, which I've wiped down with 70% ethanol. It's a good idea to flame the lip of any bottle or flask that liquid is being transferred to or from. Working with the Bunsen burner flame at my bench, the upward air current resulting from the flame should prevent any particles from falling onto or contaminating my workspace near the burner. Before I inoculate my starter culture, I need to add the appropriate antibiotic. From a 1,000 times concentrated stock, I will add 1 microliter of the antibiotic solution per milliliter of culture media. Mix briefly, then the tube is ready for inoculation. I will use a sterile toothpick, handling it with a sterilized set of tweezers, and pick a single colony from the agar plate. I only need to very gently touch the colony with the toothpick. I can drop the whole toothpick into the culture. Always label your tubes. Shut off the flame when you're done and never leave a Bunsen burner unattended. We will incubate the starter culture overnight at 37 degrees Celsius with shaking. After you've grown the starter culture overnight, you can use it to inoculate the larger expression culture in the 2-liter Erlenmeyer flask. But first, you need to add antibiotic to the media for the expression culture. Again, from a 1,000 times concentrated stock, add 1 microliter of antibiotic solution per milliliter of culture media, or 1 milliliter of antibiotic solution for 1 liter of media. Once the antibiotic has been added to your culture media, it's ready for inoculation. Again, it's a good idea to flame the lip of your flask. You're going to inoculate the expression culture with a 1% volume of saturated starter culture, which you will have grown overnight to stationary phase. So that means for every liter of culture media for expression, you will add 10 milliliters of overnight starter culture. You're going to incubate this culture at 37 degrees Celsius with shaking. And you're going to want to induce with IPTG when the culture is growing steadily in log phase at a reasonable cell density. Not too soon and not too late. This usually corresponds to an optical density between 0.4 and 0.8. So, you want to monitor the growth of the culture. And you can do this by measuring the optical density of culture samples in a spectrophotometer. You'll need to measure these against sterile media without cells as a background reference. For the reference, you want to transfer 1 milliliter of media to a cuvette. And starting after about 2 hours of growth at 37 degrees Celsius, you can start taking samples of the culture every 30 minutes or so. Measure the optical density on the spectrophotometer. Blanking first with the reference, then measuring the optical density of the culture. When the cell density is just right, you can induce expression with the addition of IPTG from a concentrated stock, usually to a final concentration of around 0.2 millimolar, give or take, depending on your specifications. Then return the culture to the shaking incubator for expression. This is often done at reduced temperature, 18 degrees Celsius for example, to ensure proper protein folding. Incubation time may vary. For example, you may leave it overnight, but again, this depends on your specifications. After you've allowed the cells to express protein, it's time to harvest them. Transfer your cultures into the large high-speed centrifuge bottles. You need to make sure that the tubes are balanced in weight. Within 1 gram is okay. If you need to, you can fill a centrifuge bottle with water to balance the tube containing your culture. When the tubes are balanced, place them in the centrifuge fitted with the appropriate rotor so that the balanced tubes are positioned opposite one another. This is very important for proper balancing. Close the centrifuge and run it at 6000 G for 30 minutes at 4 degrees Celsius. Make sure you have the proper training with this centrifuge before you use it. Once the spin is complete, your E. coli cells should form a pellet at the bottom of the tube. Discard the supernatant by decanting it back into the flask. You can sterilize this with bleach or Virkon or by autoclaving before disposing the liquid and washing the flask. You can save the pellet for later protein extraction and purification by transferring the pellet to a 50 milliliter Falcon tube and freezing it at minus 20 degrees Celsius. Or you can proceed to the next steps immediately. For the subsequent purification by nickel affinity chromatography, you are going to need to prepare a wash buffer, and you'll also need to prepare an elution buffer that contains a high concentration of imidazole. The wash buffer is essentially the same as the lysis buffer, in which you will resuspend the cells and break them open, but the latter has a few additions. For the lysis buffer, you can pour into a Falcon tube 20 to 40 milliliters of wash buffer for a cell pellet from 1 liter of culture. To this, you will add lysozyme, which facilitates cell lysis by degrading the cell wall, RNase and DNase to digest the nucleic acids in the cell lysate that can interfere with purification, and a protease inhibitor cocktail to prevent unwanted degradation of your recombinant protein. You could add these components to the buffer from stock solutions to the concentrations indicated in your written protocol. However, these usually keep better when stored as dry powder rather than as stock solutions, so I'm going to show you an alternative. You can take a small amount of lyophilized lysozyme, RNase, or DNase from the container using a clean pipette tip, and the powder that sticks to the tip is enough for the purposes of cell lysis. We don't need to be too precise. Finally, we add 1 tablet of the protease inhibitor cocktail. The tablet may take a little while to dissolve after inverting a couple of times, but once it does, the lysis buffer is ready. Next, I'm going to add the lysis buffer to the cell pellet that I just took out of the freezer. Since it's still frozen, I'm going to let it thaw for a few minutes before resuspending the cells. I resuspend the cells by mixing on a vortexer. It will probably take a few minutes before the cells are completely resuspended from the pellet. There are a couple of ways that you can lyse E. coli cells, and I'm going to show you how to do it with a sonic cell disruptor. We want to avoid overheating the sample when we use this, so we're going to prepare an ice water bath. It's important that you have water in this bath and not just ice, since it helps the heat transfer. The sonic cell disruptor uses ultrasonic pulses to break cells, so it is important to use ear protection. Make sure the probe is submerged in the sample and the tube is in the ice water bath. Turn on the cell disruptor with the desired settings. The instrument will go through cycles of pulses and cool down, which will take several minutes to complete. Before proceeding with the next steps, now is a good time to take a few microliter sample from the crude lysate to run on an SDS-PAGE later. It's good practice to take samples throughout the procedure, so you can check afterwards how your protein purification has gone at each stage. Transfer the crude lysate to a 50 milliliter high-speed centrifuge tube. And don't forget to label it. Make sure you have a balance for the tube. I'm filling another centrifuge tube with water for that purpose. Fit the rotor into the centrifuge. Place balanced tubes opposite one another. Screw the rotor lid on securely. Close the centrifuge. Set the speed to 15,000 G and run for 30 minutes at 4 degrees Celsius. Insoluble cell debris will form a pellet at the bottom of the tube. You can collect the soluble fraction by decanting, and you can further remove any particulate matter by passing it through a 0.45 micron syringe filter. At this stage, we're ready to perform immobilized metal affinity chromatography, or more precisely in this case, nickel affinity chromatography. I'm going to show you two ways to do nickel affinity chromatography. You can do it using a simple gravity column loaded with nickel NTA agarose, or alternatively, you can use an FPLC instrument that pumps a steady flow rate through a more specialized column. First, I'm going to show you the simpler method using gravity columns. This doesn't require specialized equipment, but it's usually slower than FPLC because the flow rate is determined by gravity. And it's not as good as FPLC at resolving the desired protein from potential contaminating proteins, since unlike FPLC, it cannot deliver a smooth buffer gradient. But it is straightforward, and you can process many different protein samples simultaneously. The first thing we need to do for nickel affinity chromatography by gravity column is to pack a column. Taking a 50% slurry of nickel NTA agarose, I'm taking 2 milliliters of suspension and adding it to the column. As the liquid drips out the bottom, it leaves a 1 milliliter bed of resin. Then I need to equilibrate the resin, which had been stored in 20% ethanol, with my wash buffer. I add 2 to 5 milliliters of wash buffer and let it drip through. Now I can pass the soluble cleared lysate through the column, making sure to collect the flow-through, which I will analyze by SDS-PAGE later on. The column only has a 10 milliliter capacity, so I will probably need to pass the cleared lysate through in more than one batch. I almost forgot to take a sample of the soluble cleared lysate for SDS-PAGE analysis. I'll do that now. Good thing I still had more in the tube. I'm adding the remainder of the cleared lysate in the second batch. Next, I'm going to pass 5 to 10 milliliters of wash buffer through the column once or twice to wash away any unbound protein, which should leave our his-tagged protein bound to the nickel NTA agarose beads. I'll collect the wash fractions also to analyze later by SDS-PAGE. I'll do a second wash now. Now I can elute my protein with the elution buffer, which contains imidazole. I will elute the protein over several fractions. I'm going to collect 2 milliliter fractions. After the purification, you can save the resin in the column for later reuse. If you are purifying a different protein and want to avoid any possible contamination, a stringent wash procedure may be necessary. So the other method of nickel affinity chromatography is with an FPLC instrument using specialized columns that look like this. These columns can withstand the pressure that the FPLC delivers, but can't be loaded by gravity. Instead, you can load them either by syringe with an adapter or by a peristaltic pump. Here is one such column being loaded using a peristaltic pump. You need to be a little careful to prime the tubing lines with liquid before connecting your column to avoid pumping air into the column, which you don't want. And also, unlike gravity columns, once all the fluid has passed through, air will continue to be pumped through the lines, so you need to watch the level of liquid carefully. After passing the cleared soluble lysate through the column, you can also run a wash with the peristaltic pump. You can then connect the loaded and washed column to an FPLC instrument, which has been primed with both wash buffer and elution buffer. Starting the program will run a gradient with steadily increasing imidazole from the elution buffer. This can give you a better purification since different proteins may elute at different points in the gradient, separating your desired protein from undesired proteins. The run is also fast since you can control the flow rate, and the instrument monitors UV absorbance by proteins, so you can tell in real time which fractions contain more protein. But you will still need to do analysis by SDS-PAGE to check where your desired protein is and which fractions are pure. Remember that in addition to my elution fractions, I collected samples from the crude lysate, the cleared soluble lysate, the flow-through, and the wash. It's time to analyze my samples by SDS-PAGE. I have taken a few microliters from each and heat-treated them after adding SDS loading buffer. Any of the samples that have insoluble material in them should be vortexed vigorously for a minute or so, and any remaining insoluble material removed by centrifugation before running them on a gel. I'm using a precast 4 to 12% gradient gel. Don't forget, in addition to your samples, you need to load a molecular weight marker. I'm going to load my gel first with my samples from crude lysate, cleared soluble lysate, flow-through, the first and second washes, then molecular weight marker, followed by the samples from my elution fractions. Connect the gel tank to the power source and run at 200 volts for about 25 minutes. When the run is complete, you can remove the gel from its casing. You may need to be careful about the orientation of the gel in case it becomes flipped and you get confused about the order of the samples, but it should be easy to tell by where you loaded the molecular weight marker. Stain the gel with Kumasi solution for half an hour to an hour. You can save the old Kumasi solution for reuse. Then, destain the gel for a few hours. You can speed up the destaining process with a cotton ball to absorb the Kumasi stain. After destaining, you can check which fractions contain your pure protein and then pool them. You can then concentrate the pooled protein solution prior to carrying out buffer exchange, since the elution buffer may not be optimal for the storage or activity of your protein. I'm using a centrifugal filter with a molecular cutoff of 30 kilodaltons to concentrate my protein. Proteins above this size remain above the filter, but the buffer can pass through when the filter is centrifuged. You can balance the centrifugal filter with a falcon tube filled with water. Spin for a few minutes based on the manufacturer's protocol and your desired final volume. For the buffer exchange, I'm going to use a size exclusion column in a desalting procedure that requires a sample volume of less than 3 milliliters. First, I need to equilibrate the column with the buffer in which I will store my protein. Here you can see the centrifugal filter after it's spun. My protein sample remains on top in a reduced volume of buffer, and on the bottom is buffer that passed through the filter. Then, with 3 milliliters or less of concentrated protein sample, I can load this onto the size exclusion column equilibrated with storage buffer. The gel resin in the column contains many small pores and channels. Salts are small enough to enter the pores, but proteins are not, so they flow around the beads. The result is that proteins will elute from the column first, while the salts and buffers from the applied sample are retained on the column longer. This way, proteins can be separated from the sample buffer and eluted with the buffer in which the column was equilibrated. Use the column according to the manufacturer's protocol to get your protein into your buffer of choice. If done right, your protein will elute in the collected volume while the salts remain on the column. And finally, after measuring the protein concentration, you can store the protein sample in the fridge or at -80 degrees Celsius for longer term storage.